Brooke Taylor was born at the end of the 17th century to parents in the English aristocracy. Educated in schools in London, Taylor took an interest in math and science from an early age. At the age of 23, Taylor published a groundbreaking work in physics. This work is credited with solving a modern-day problem with the vibration of strings. From the notoriety from this work, Taylor was elected into the Royal Society of London, whose members included Sir Isaac Newton, who became a very close friend of Taylor's. The society became involved in a dispute involving Newton over who developed calculus. Isaac Newton and Sir William Leibniz are both claiming credit for developing calculus, and the Royal Society got involved, and Taylor sided with Newton, who was his friend. However, Taylor was criticized by his peers outside of the Royal Society for supporting his friend for this conflict of interest. After the society sided with Newton, Taylor published a work on perspective, which has to do with three-dimensional drawings in art. Taylor was able to show and prove that there's a point he called the focal point, where we can draw three-dimensional drawings on two-dimensional surfaces by using this point as a center point. After perspective, Taylor became involved in a dispute himself with Bernoulli over the development of what became known as Taylor series. This dispute caused Taylor to stop working on mathematics at the young age of 34, and Taylor died a couple years later, leaving behind only one daughter named Elizabeth. Taylor's most significant contribution was that of Taylor series. Taylor series is the process that allows mathematicians to evaluate difficult functions. Taylor called them transcendental functions, such as y equals sine x, y equals cosine x, y equals log x, by using the nth derivatives of polynomials at a certain point. For example, here in this picture, we have the curve y equals sine x. We have a linear function y equals x. And then we have a polynomial function in blue. Taylor is using the polynomial function, the derivatives of it, to estimate the value of sine x. You can see this polynomial function has the same values as y equals sine x from -4 until 4. Taylor realized that we could use these polynomial functions to estimate these transcendental functions as long as the points coincided. Taylor series is now programmed into modern-day calculators. For example, in calculus, if a kid wants to know the sine of 28 degrees, they'll just grab a calculator, hit sine 28 degrees equals. They will be given a long decimal approximation of the sine of 28 degrees. The calculator is using Taylor series, or the nth derivative of a polynomial function around 28 degrees, to come up with this decimal. Also, scientists are able to model nonlinear water movements with trig functions, and Taylor series allows us to evaluate these trig functions. Finally, the best application of Taylor series is it makes differentiation and integration of difficult functions easier, because we can substitute polynomial functions in for difficult functions and differentiate or integrate the polynomial function, which of course just requires the power rule, which is simple to use. Taylor's contribution in mathematics was very significant and is widely used today.